Pythagoras of Samos was an ancient Greek philosopher, mathematician and mystic. To begin this lecture, I would like to demonstrate how the mathematics, philosophy and mysticism of Pythagoras gave rise to the tuning system that bears his name. This diagram shows the famous Pythagorean tetractys, which has the numbers 1, 2, 3, 4 arranged in an equilateral triangle. The tetractys demonstrates the Pythagorean belief that the universe was made up of numbers. The number 10 is a triangular number in which 1 plus 2 plus 3 plus 4 equals 10. Thus, the tetractys contains the ratios needed to produce a musical scale. 2:1 being the octave, 3:2 a perfect fifth, and 4:3 a perfect fourth. The mystical philosophy of Pythagoras that states the universe is controlled by numbers may be perfectly illustrated using the monochord. The monochord has a fundamental string through the middle with another string on top with a movable bridge. If I place the bridge halfway down the string to give a ratio of 2:1, we get the musical interval of the octave. If I move the bridge to 2/3 of the string length, we get the musical interval of the perfect fifth. If I move the bridge to 3/4 of the string length, we get the interval of the perfect fourth. If we imagine a perfectly vibrating string that can sound all of its overtones, the first overtone would be the octave. This octave overtone would have its own overtone of an octave, etc. For the fifth overtones, the second overtone would be an octave plus a fifth. This overtone would itself have an overtone of an octave plus a fifth, etc. Pythagorean intervals may be formed as the product of the naturally occurring fifth and octave overtones of the harmonic series. A Pythagorean interval has the form 2 to the power of A over 3 to the power of C, or 3 to the power of B over 2 to the power of D, where A, B, C, D are integers or 0. The following table shows the Pythagorean intervals that I used to produce my scale. The minor second is given by the ratio 2 to the power of 8 over 3 to the power of 5. The major second, 3 to the power of 2 over 2 to the power of 3. The minor third, 2 to the power of 5 over 3 to the power of 3. The major third, 3 to the power of 4 over 2 to the power of 6. The perfect fourth, 2 to the power of 2 over 3 to the power of 1. The augmented fourth, 3 to the power of 6 over 2 to the power of 9. And the perfect fifth, basically 3 over 2. Two quick examples of how to calculate these intervals are as follows. A perfect fifth is the difference between an octave and a fifth and an octave, that is to say 3 divided by 2. A major second is the difference between 2 perfect fifths and an octave, that is to say 3 over 2 to the power of 2 times 1/2. Number theory tells us that all integers may be expressed as a product of prime numbers. Thus, I equals prime 1 to the power of A times prime 2 to the power of B times prime 3 to the power of C, etc. I is an integer, P1, etc. are prime numbers, A, B, C, etc. are integers. Example 1 shows that 360 is equal to 2 to the power of 3 times 3 to the power of 2 times 5 to the power of 1. Example 2 shows that 2,400 is equal to 2 to the power of 5 times 3 to the power of 1 times 5 to the power of 2. The numbers 2 and 3 are said to be relatively prime. Their only common factor is 1. Thus, there is no ratio 2 to the power of A over 3 to the power of C, or 3 to the power of B over 2 to the power of D that corresponds to the ratio 2 to 1 or its compound. Since the numbers 2 and 3 are themselves prime numbers, if we increase the powers of 2 from, say, 2 to the power of 1 to 2 to 3 to 4, and we did the same to the powers of 3, we would not introduce any new factors, merely more 2's and 3's. This means that there is no fraction 2 to the power of A over 3 to the power of B, or 3 to the power of C over 2 to the power of D that corresponds to the ratio 2 over 1. This fact gives rise to the Pythagorean comma, which is the difference between enharmonic notes. If we cycled round a circle of fifths to end up on B sharp, this would be equivalent to 3 over 2 raised to the power of 12, which is slightly sharper than 7 octaves, the note C, which would be given by 2 raised to the power of 7. Thus, the Pythagorean comma is equivalent to 3 to the power of 12 over 2 to the power of 19, an interval corresponding to approximately 23.46 cents. The Pythagorean comma and the lack of equivalence between enharmonic notes has had profound implications for the tuning systems used throughout musical history. Musical theorists have used various methods to temper the basic Pythagorean scale so that it remains in tune when the music modulates to remote keys. For example, our modern equal temperament tuning has each semitone exactly the same ratio, the 12th root of 2. I have become increasingly frustrated with the bland mechanical sound of equal temperament tuning. Thus, I have tried to produce a scale which gives me the pure sound of the Pythagorean intervals, but remains in tune as much as possible as I modulate to remote key areas. Whilst I very much admire and enjoy listening to the music of complex composers such as Brian Ferneyhough, James Dillon, Elliott Carter, etc., I have come to regard such music as like white noise. It has a chaotic surface but lacks deep structure. It has no musical syntax or semantics. To a certain extent, my compositional style resets the dial on musical theory to explore a kind of postmodern, post-tonal, polyphonic style. This is an attempt to produce music that has deep structures, that has syntax and semantics. Since my music explores the fundamental relationships between notes in terms of intervals and harmony, I am increasingly frustrated with the bland, mechanical equal temperament tuning. Thus, I am trying to develop a tuning system which has the smooth, pure-sounding Pythagorean ratios, but stays in tune as much as possible when I modulate to remote key areas. The method I used to produce my scale is very simple. I took a starting note and applied the Pythagorean ratios described earlier, corresponding to the minor second, the major second, the minor third, etc., up to the interval of the perfect fifth. From this perfect fifth, I then reapplied the same ratios up to another perfect fifth, and then repeated this process to give me the scale. Logic tells me that as I modulate to each new key area in a circle of fifths, the intervals will more or less stay in tune with the original Pythagorean intervals. As the scale progresses upwards in pitch, certain ratios are a whole amount of the Pythagorean comma out of tune with the original Pythagorean ratios. There are no enharmonic notes in my scale, just approximations for various pitches. This diagram shows how the scale was generated. The scale was designed to tune a standard 6-string guitar. After trial and error, I decided the best starting pitch was an F, the first fret on the 6th string or the top string of the guitar. This corresponds to a pitch of 85.33 Hz. The ratio column shows whether the increase is by a diatonic or chromatic semitone. The fraction column shows the increase in terms of a Pythagorean interval. The cents column shows the increase in pitch measured in cents. I would appeal to the musical community, the performers, the composers, the music theorists, to reject equal temperament tuning with its mechanical outlook and its attempt to control nature. I would like to see the rewilding of music, a sort of musical ecology which restores as many different tuning systems as possible. For general musical usage, I would advocate something like my scale as a standard, but solo performers like guitarists or pianists or string quartets could employ a variety of tuning systems even within one recital. This would reintroduce variety in the tuning systems that we use and would work with nature, not against nature. The scale that I have shown you is perfect for my own uses in my postmodern post-tonal polyphony. Each octave transposition brings with it a slightly altered set of ratios, a new sound, a new flavour. The same is true when you modulate to different key areas. The first piece I composed using my scale was a quartet for 4 guitars entitled New Tuning. This piece uses a slightly different version of the scale that I showed you today and uses a reference pitch of A at 440 Hz. I tuned the 6 open strings of the 4 guitars to a different note of the scale and used these notes to compose the piece. The piece modulates to remote key areas, but more or less sounds in tune in these remote key areas. This is an extract of a piece I am working on at the moment called Sallisian Tuned Guitar 1. To realise the piece, I recorded each individual note of the scale into Logic Pro and used Logic Pro like a sampler to realise the music. Eventually, I will orchestrate the piece for a solo guitar using just open strings and harmonics with no fretted notes. Sallisian Tuned Guitar 1 uses the scale that I've shown you today with a reference pitch of A at 432 Hz. I chose this reference frequency because 432 is equal to 2 to the power of 4 times 3 to the power of 3, which seems Pythagorean in nature. would my scale fare when used for the performance of historical music? For music up to the early 16th century, this would be no problem, since my scale is essentially a Pythagorean scale. For music from the early 16th to the early 17th century, the out-of-tune notes in my scale approximate to mean tone just intonation. Thus I predict most music from this period would sound absolutely fine in my scale, given the limited modulations you find in such music. For the playback of Queen Elizabeth, Her Galliard by John Dowland, I used Logic Pro like a sampler in a similar fashion to Sallis tuned Guitar 1. I chose this particular piece because it is quite chromatic and passes through E major, E minor and G major. This diagram shows how the intervals of the Pythagorean scale may be expressed as a sum of diatonic and chromatic semitones. Thus, the minor second is a diatonic semitone, the major second is a diatonic plus a chromatic semitone, the minor third is 2 diatonic plus 1 chromatic semitone, etc. The nature of my scale is such that each key will be perfectly in tune in at least 1 octave transposition. Therefore, to give a representative example of how in tune or out of tune various keys are, I have shown the keys from C3 to C4. The black notes are in tune and the red notes are out of tune with the original scale. Whilst the previous diagram did contain a lot of red, this diagram shows significant notes out of tune with the original scale. As you can see, you could happily modulate to most keys without having to worry about being out of tune with the original scale. Since my scale is not in any way tempered, even the so-called out-of-tune notes are Pythagorean intervals and thus would be part of the naturally occurring overtone series. Thus, rather than out of tune, the notes would merely sound different in quality to the original scale. This diagram shows the altered ratios for the key of C sharp. The altered ratios are still Pythagorean ratios and, as I said before, would simply have a different quality to the original scale. For music written in the early 17th century through to the end of the classical period, this may prove more problematic when played in my scale, given that some of the octaves are out of tune in various octave transpositions. However, I would still predict that most music would sound absolutely fine when performed in my scale. To realise this famous Bore by Bach, I used Logic Pro in a similar fashion to the other pieces. I chose this particular Bore because it is very chromatic in nature. It uses all 12 semitones. tonal music of the 19th and 20th century, written in equal temperament tuning, would not sound so good when performed in my scale. It just so happens this is a musical period that I very rarely ever listen to. Whilst my scale does suffer from the usual problems associated with tuning systems based on Pythagorean intervals, that is to say, out of tune octaves and remote keys being more out of tune than other keys, it does have the advantage that, since no intervals are tempered, every interval is a Pythagorean interval and thus part of the naturally occurring overtone series. Pythagorean philosophy and mysticism demands that the scale be based on the ratio of the octave 2:1. However, I'm prepared to sacrifice Pythagorean mysticism for good musical practice. The octave is possibly the least interesting interval in the lexicon of musical intervals. It merely doubles a pre-existing pitch. Thus, if we abandon the attempt to keep octaves in tune, we have a circle of fifths which will preserve Pythagorean intervals, and thus all intervals will be part of the naturally occurring overtone series. Thank you for listening to this lecture, and many thanks to Augustine and the committee for organising this conference. If you would like any of the charts and diagrams I have shown, please get in touch via email or Facebook and I can send them to you. If you would like to critique what I have said today and suggest improvements, please get in touch. If you would like to talk about anything whatsoever, if you would like to talk about the weather, please get in touch. Thank you.